In this video, we will be talking about row echelon form, Gauss's elimination, and Gauss-Jordan method. So let's begin with the definition of row echelon form. What is row echelon form? Any matrix after a sequence of elementary row operations, which we studied previously, gets reduced to what is known as the row echelon form. In this form, each row, except perhaps the first, starts with a string of zeros. Each row starts strictly with more number of zeros than the previous row. So what do I mean with this? Let us take an example of a row echelon form. 1 0 0 0 2 0 0 0 3. This particular matrix is actually in row echelon form. This is a matrix in row echelon form. Now, let us take an example wherein we convert a given matrix into row echelon form. So, as I told you in the last video, performing elementary row operations is equivalent to multiplying a given matrix A by a certain elementary row operation matrix. This is essentially how we do row operations on matrices in algebraic terms. So let us take the example of a 3 cross 3 matrix, say 1 1 2 3 1 4 0 1 2. Let us call this matrix A. So now let us cleverly perform some row operations to reduce it into row echelon form. So as we know, this is 0. This last element is 0. So for row 2, let's write row 2 as row 2 minus 3 times row 1. So A actually becomes 0 minus 2 minus 2 0 1 2 1 1 2. Now we can see that the first column is in row echelon form. Let's talk about the second column. Let's write row 3 as row 3 minus 1 by 2, actually plus 1 by 2 times row 2. So we will get A is equals to 1 1 2 0 minus 2 minus 2, and this will become 0. This will also become 0 because 1 by 2 multiplied by minus with minus 1 added to this is this. This will become 1. Now this particular matrix is actually in row echelon form. How are we saying this? It obeys every single condition. And these numbers that I'm highlighting, these are known as the pivots of the row echelon form. There is another added thing known as reduced row echelon form. What is this reduced row echelon form? It is nothing but row echelon form converted into a rather nifty way. So nifty way of writing. So we make all the pivots as 1. So 1 1 2, we multiply the second row by minus 1 by 2. This becomes 0 1 1 0 0 1. Now let's begin with the second topic, which is Gauss's elimination. What is this Gauss's elimination? Say we have a system of equation Ax is equals to B. As we did in the previous video, Ax is equals to B is actually a very nifty way of representing certain linear equations in several variables. Now, how do we go on about solving this equation, solving this system of linear equations? What we do is we multiply an elementary row matrix by A, and we multiply it by B here again. So the same operation is performed on B as is performed on A. And by doing such operations, we eliminate the system of linear equations quite steadily, I might say, quite smartly and in a clever manner, such that we have such that we don't have to back substitute and we can easily get the values of the equations. So let us take an example for this. So here is our example. We have 4 different equations. So let me write them in terms of a certain coefficient matrix known as A. So for the first equation, the coefficients are 1, minus 1, 1. Second, it's minus 1, 1, minus 1. Third, it's 0, 10, 25. Fourth, it's 20, 10, 0. X matrix is just x1, x2, x3. And B matrix is 0, 0, 90, 80. So what we do now is we create an augmented matrix. Remember augmented matrix? Augmented matrix. So we write augmented matrix like this. 1 minus 1, 0, 20, minus 1, 1, 10, 10, 1 minus 1, 25, 0. With B just here, let me just write this properly actually. So properly we write it like this, 0, 0, 90, 80. Now let us perform some elementary operations on this matrix to reduce it to row echelon form. So how do we reduce it to row echelon form? As we learned previously, we write row 2 dash is equals to row 2 plus row 1, and row 4 dash is equals to row 4 minus 20 times row 1. So let's see what happens now. After performing these operations, we get 0 here. We just add, so this also becomes 0, this also becomes 0, this also becomes 0. This becomes 0, this becomes 10, this becomes 25, this becomes 30, this third row remains the same. For the fourth row, this becomes 0. So we multiply it by 20, and then this actually becomes 30 right here. This becomes minus 20, and this remains as 80. Now since we know that the first column is now in row echelon form, if we write it like this actually, if we just write it again like this, 0, 30, minus 20, 80, 90, 25, 10, 0, 1, minus 1, 1, 0. Now let's perform the other row operations. So we write row 3 as row 3 minus 3 times row 1. Let's see what happens. 1 minus 1, 1, 0, 0, 10, 25, 90. Subtract 3 times, this becomes 0, 75, this actually becomes 55, or no, wait, this becomes 95 actually. This becomes 95, this becomes 80 minus 270, so that is 190. This is it, right? Now, as you can see, this is clearly in row echelon form, isn't it? This is in row echelon form. Now, what do we do? What we do is we multiply these equations by their corresponding variables. What do we mean by that? This corresponds to x1, this corresponds to x2, this corresponds to x3. So this means 95x3 is 190. This means x3 is actually 2. Now, since we found x3 to be 2, we do the same with the second equation. So 10x2 plus 25x3 is equals to 90. Hence x2 is equals to 90 minus 50 by 10. And that is 4. And lastly, we write x1 minus x2 plus x3 from the first equation, x1, x2, x3 is equal to 0. Hence x1 is equals to x2 minus x3, which is 4 minus 2, which is again 2. So now we have found out actually the values of x2 as 4 and x1 as 2. So now if we go on up and substitute these values, say we make x1 is 2, x2 is 4 and is 2, so we can see these values actually go on to satisfy our given conditions. So we have done by elementary row operations, we have eliminated this system. So this is what Gauss's elimination is about. Now lastly, let's just quickly discuss Gauss's Jordan method to find inverse. Gauss-Jordan method to compute inverse. So this actually is very interesting. It works on the same concept of these elementary row operations. How does it work like that? Say I have a system of equations IA is equals to AI. I can multiply the identity matrix is commutative, so I can write it like this. Now say I perform some row operations on, actually let me just write it like this. Let me write it like AI is equals to IA. So I perform a certain set of elementary row operations on A, and the same set of elementary row operations I perform on the identity matrix. And let's say finally I convert this into the identity matrix as we saw above in the reduced row echelon form. Then this equation will actually become like this. And hence we would have computed the inverse of A. What is inverse of A? Inverse of A is just A in, so when we multiply A by its inverse is it becomes equal to the identity matrix. So this is just the definition of inverse. So this is the definition of inverse of a matrix. How does all this work? Let us take an example. Now in this example, let us write the equations we want. We write AI is equals to IA. So we are just actually worried about the identity matrix, right? So minus 1, 3, minus 1, 1, minus 1, 3, 2, 1, 4 is equals to 1, 0, 0, 0, 1, 0, 0, 0, 1, A, I here. Now let us start doing our mathematical wizardry and performing some operations which we do. So first what we'll do is we'll make row 2 is equals to row 2 plus 3 times row 1. We'll make row 3 as row 3 minus row 1. So this work gives us a workaround for our first row. This becomes 0. We add 3 times the first row, so this becomes 2. We add 3 times, so this becomes 7. And this becomes 0 again. We subtract, this becomes 2, this becomes 2. So I is equals to, now we perform the same operation on the identity matrix. How does that work? So this becomes 3, this becomes 1, this becomes 0, this remains 1, 0, 0. We subtract it, so that's becoming minus 1, 0, and 1. Now what do? We perform the same thing on the second row. So we write row 3 dash actually as row 3 minus row 2. What will that do? That will help us again. Minus 1, 1, 2, 0, 2, 7, 0, 0, minus 5. I is equals to 1, 0, 0, 3, 1, 0, minus 4, minus 1, and 1. This is exactly what's been happening here. Now let us actually make this into the identity matrix. So first we'll have to take minus 1, we'll have to multiply the first row, row 1 dash, by minus 1. Secondly, we have to make row 2 dash as 1 by 2 times row 2. And thirdly, we have to make row 3 dash as row 3 by minus 5. So let's perform all these operations as well. So this becomes 1 minus 1 minus 2, 0, 1, 7 by 2. This becomes 0, 0, 1. I is equal to, from the same things on the identity matrix as well. So this becomes row 2 is 3 by 2, 1 by 2, 0. This is 4 by 5, 1 by 5, minus 1 by 5. Okay. Now we just have one last little step remaining. We have to convert this into the identity matrix, right? So we'll write row 2 as row 2 dash minus 7 by 2 times row 3. and we write rho 1 as rho 1 dash as rho 1 minus rho 1 plus 2 times rho 3. So what will happen now? Let's see. So from 1 minus 1 0, so from 0 1 0 0 0 1 I is equals to, now rho 2 dash is equals to rho 2 minus 7 by 2 times rho 3. So 7 by 2 times rho 3 is 28 by 10 minus 28 by 10. This is minus 13 by 10. And similarly, minus 7 by 2 times rho 3. So this becomes 7 by 10 here. This third element becomes 7 minus 7 by 10. This becomes minus 2 by 10. This is 4 by 5, 1 by 5, minus 1 by 5. And we have done the same thing on this row as well. So this becomes minus 1 by 5, 1 by 5, minus 1 by 5 times in. And one last operation is rho 1 dash is equals to rho 1 plus rho 2. This will make this into the identity matrix. This will make this into inverse. And this is what we have finally. So finally we have computed A inverse. What does A inverse look like? So as you can see, A inverse actually looks like this. And this was the Gauss Jordan method for inverse. So this is actually very important in mathematics. Actually, all computer systems like MATLAB, Simulink, Octave, these actually use these types of algorithms to compute inverses.